Welcome back to our SICP videos. We're going to do the Newton squares in Clojure, and it's going to be basically transcribing the scheme code from the book, the original scheme code, directly into Clojure. So it's a very basic translation video here. And the way I'm going to do it is start with the smallest helper functions to the slightly more complex helper functions, and not actually show our real, square root function until the very, very end. So here we go. We're going to first do our obligatory namespace declaration. Then we're going to just knock out our helper functions. This is just basic pieces of math here that I could certainly just import in, but I would rather build them from scratch. So an arithmetic mean of two numbers is you take the sum of the two numbers and you divide it by 2. This is prefix notation. You should definitely get to know this if you're not familiar with any Lisps. But if you're watching this video, I'm sure you're familiar with them, so you'll be fine. Our next little utility is going to be square, just returns square, and our absolute value. Absolute value, if you've never seen this formally specified in proper mathematics, looks basically like this. It is always a conditional. It multiplies its argument by 1 if its argument happens to be less than 0. Otherwise, it just doesn't do anything. There. So on to our smaller functions. Definitely more complex than our utilities, but not nearly as complex as our actual square root function. This is just going to make up a piece of what makes the square root function. The first one we're going to do is our improve. This one will improve the guess. It takes these two arguments. And the way it works, this is a little math trick that Newton came up with, where you take the average of guess and the quotient, x over guess. This will make a baby step toward making this guess work a little better. The next thing we do is this good enough question, which it basically is a Boolean situation. We're comparing an order. We're comparing an order. We're going to say, is this function here, what it looks like is it's an absolute value of the difference between our square of the guess and x. And we're going to compare that to see if it's less than some number p. P is our precision measure. It's how we measure precision. It'll look a little something like this. I can just declare it as a constant up here. So our good enough is going to return either true or false based on this comparison, this less than operation. Great. So at this point, this is one of the first truly great recursion in the whole book. Recursion, the best way to understand recursion is to start with your escape condition, basically. Very strictly, this is called a base case. This isn't really a base case, but it's still our escape that lets us not have a stack overflow here. So it's our iteration through our square root. It's our square root iterator, and every time it goes through it's going to improve the guess. Meaning, one of the things we do when we call this is we call improve. You'll see that in a second. So this is going to take. Let me just keep this consistent. This is going to take two arguments, x and guess, just like all our others. And this is the important part about recursion. It starts with a conditional. It's if. If you don't have some form of conditional in an implementation of recursion, you're going to like always be in a never-ending situation. Always going to be in a Stack Overflow. So you call good enough, right? Because good enough will return a Boolean. If it returns true, then you just return that guess, right? Because that means the guess is good enough. That means according to how finely we need to approximate, we're good enough. Otherwise, if we're not good enough yet, we gotta iterate through again. So we're going to call ourselves. We're in the function square root iter, and we call iter. This is just recursion. It's just self-reference. There's a Robert Harper blog post where he says recursion is what it is and nothing else. It just is what it is. It's this self-reference thing, but we're going to call it not just on X guess again, but on an improvement of our guess. So what this function composition would look like is if square root iter was S and improve was I. What this would look like would be S, compose I. I don't have the little circle that we use for compose, but I'll just use the dot. At the tuple xg. That's basically which looks like S I xg. Just a little math reference there, but I'm sure you can follow that. So here we are. Now we are all set up. We have defined how we escape our recursion. Given this, when this is Boolean true, we're done. This is our recursive step. And we have all of our mathematical utilities. We have this little improvement equation that, this improvement function that Newton came up with. Now we recur, essentially. We just get our square root x. I'm just going to pass it a single x because we're going to initialize this on a starting guess of 1. We just start with 1 and work from there. That is really where we get how we happen. So this is it. This is our code. That's all it takes. And let me just fire up a REPL. It's gonna take a few seconds. REPL is read eval print loop. If you've not seen that before. And all right, here we are. We are up. So what I need to do is I need to ns Newton to say that my loop, my read eval print loop is in this namespace. And I'm going to basically send all my functions to my REPL with this little Emacs command, cck it was, and check it out. We have sqrt4. And, ooh, arity exception. Wrong number of args passed to Newton square iter. Okay, so, excuse me. Square iter had the wrong number of arguments passed to. I wonder how that happened. Because, oh, see, look what I did. It was called here. It was fine, but called within itself, it was not fine. It needs to be called on X and an improvement of its guess. So, okay, still didn't work. Oh, why? Because I didn't CX, CK. Every time you gotta, okay, excuse me. Bang, look at that. Oh, well, okay, wait, that's not right. That is a rational number. Why is it a rational number? Because 4 is an int. I believe, can I do type 4? So, okay, so it's a long, right? And I think I can do this. Well, it would be type divides this number and this number. that's a ratio. So it knows it's a rational number essentially. Now this might not be what I want to look at, right? Like this is I want this to be 2. So what I can do is I can take this number and I can cast it to double, right? Double is very similar to float. A lot of the technical is very similar. Just double is just made for more precision, more to store more digits. And I mean, these days, you know, our computers tend to be built powerful enough that it's fine to use doubles all the time, even when it's overkill. So that's what we're going to do. We need somewhere in here. I mean, we could of course expect the user to type 4.0, right? But why don't we put something in our code that will kind of make it better for us? Why don't we, in one of our functions, actually do the conversion? Why don't we go in here, double X, right? So this is going to do the conversion when I first call it, and from there it'll be now. If you know anything about how like arithmetic works in computers, if I have 4.0 divided by 2, that returns 2.0. If one of my numbers is a float, they're all going to be floats. So I'm going to do this cast. Let me just CCCK SQRT 4. Would you look at that? We are what is called arbitrarily close to 2. Basically, the limit as this p-value goes to 0. The limit of our square root function as p goes to 0 approaches 2. I think there's just very interesting subject here, just a tangent about double arithmetic, floating point arithmetic. In theory, that's the limit. The limit as square root of 4, the limit as p approaches 0 of square root of 4 is 2. But in practice, my computer won't actually do it because this algorithm is really not going to be designed for specification above this. You know, I mean, we can round it, of course, and it's fine. We can even, in this case, truncate it. But just something to keep in mind. You know, floating point numbers are not real numbers. They're very different. Floating point numbers can just make approximations. That's all they're good for. That's all they really are. So let's just test this on more. Take 8 somewhere there. SQRT 256 is, look at that. It's very close to 16. The famous, scorn of the Pythagoreans, square root of 2. So there we have it. We have Newton's method, Newton's little scheme. I guess they call it his algorithm to find the square root of a number. Thanks very much. I will be back with a Java implementation. We will see mutable data structures carrying out the same thing. It's going to be a very different implementation. Stay tuned.